Hello everybody and welcome to the 7th session of our electrophysiology trainee workshop. Today's topic is gonna be programming, and the idea is to talk a little bit about a couple of concepts in programming that are gonna help you mostly structure your own work, help you to avoid making mistakes and having to correct them later on, and also make it easier for you to collaborate with other people. And yeah. And next week's session is gonna be some live coding where we're gonna do some data analysis, and that starts from basically downloading Python and goes all the way to seeing some kind of results. And I wanted to start this session with an example of like really bad code, and this is basically the worst code I managed to come up with. And this code has basically everything wrong that could have been done wrong in the first place. So, and the most glaring issue with this code is that literally the whole code sits in a try and catch block. And I've actually a lot of people seen doing that. And what this try and catch block around your code does is, when you run this code, your computer tries to execute one line after the other, and in case there's an error, it basically stops. Let's say here, the error happened here, but you're not getting an error message or anything the like. It just goes on and doesn't execute the last couple of lines after that anymore, and that's like really dangerous. And you should, whenever writing code on your own, you should really try to avoid doing try and catch stuff, except unless absolutely necessary. And the next thing that's wrong with this demo code is that, it's Python code, and in Python you import functions, but that's something you can do pretty much in any programming language, maybe the Java or C. You can always import specific files. And what I did here is I imported the stuff always at the moment when I needed it, and I didn't structure it in some kind of coherent way. And that's actually also not as good, because ideally you want to have your imports on the top, so everybody so that gets separated from the code you just wrote, to have that more structured, more easily to understand later on. And the next thing that's really bad with this example here is the variable names. Like, all of them are data1, data2, result1, result2, and the like. And that's actually way more common than you might actually think, because if you look at the usual code that somebody writes, then doing the first few lines of coding in their life, they always usually call their variables temp1, temp2, whatever, anything similar to that basically, and that ends really badly at some point. So renaming those and giving them proper names is something not only other people would profit from then looking at your code, but also you profit on later down the line. Because let's say you just started your PhD, for example. You're gonna do a project. The project's gonna last a couple of months or a couple of years. You're gonna sit down, write a line of code, and then like 6 months later or a year later, you're gonna have to go back to that. And you're only seeing your variables called x, y, z, and data 1, 2, 3. You have literally almost like no way of figuring out what that supposed to mean now. So giving that those proper names is something you yourself are gonna profit from highly in the end, which is basically what I then did here. The data is called data, header information or meta information is called header. Then we have the channel index here, not as a magical number in here anymore, which is actually also something a lot of people do, putting magic numbers in the code. And a magic number is a number that serves a specific functionality, but it's nowhere documented why this number is supposed to be like free or whatever. And at least by calling it channel index, I know it's supposed to be the third channel. So it's giving some information already. And what also got added here is this stamp on the top. And that basically indicates when this file was created, who created that file, and that's also later on gonna help you because you know how old the thing is in the first place. And another issue with this demo code here is that what also a lot of people do is writing codes as code as if they wrote a script, and then for example, when I did my PhD, I saw other people. I saw the code other people had written, and they, for example, had a MATLAB script, which was supposed to interact with some kind of robot, and that script had roughly 4,500 lines of code, and was and everybody was basically saying, "Don't touch it. It does something. You're supposed to press that button and adjust this and this variable according to what you're supposed to do. But do not touch any other part of that code." And that's kind of the issue with doing it like that. Like structuring your code like that. If you write this super large script, it becomes really difficult later on to have some structure in there, to understand what's going on in specific parts of your code, to deal with that, essentially. Not only for you, but also for others. If you like write some routine that's supposed to interface with an EEG amplifier or whatever, and other people are supposed to use it, they really like understanding what they are supposed to do with your code in the first place, instead of blindly following some kind of instruction. And we could partly achieve that by putting that code already in a main function, which is kind of nice, since what this file is mainly supposed to do is this stuff, so that goes in the main function. And that already serves its purpose on its own, which I'm going to expand on later a little in more detail. And then within this file, we kind of have three different concepts being in the same method now, and they are competing with one another. You have data being loaded in the first block here. You have some data being evaluated, in this case getting a power estimation in that second block. And you have data getting visualized in the third block here. And that's competing ideas. For example, loading the data is in no way inherently connected to visualizing that same data. So what you want to do actually is you want to split that into separate functions. So you have a function for loading data. You have a function for extracting a feature, in this case the power. You want to have a function for visualizing your results. And then if you, as I said in the beginning, 6 months later go back to your code and you notice that something is odd with your visualization, you don't have to scroll through that 1,500 lines of code that you wrote into a single script. You can go into the visualization function. You can try to figure out in there what's going wrong. And that's going to help you a lot in the long term. And then, well, let's go step back. That's basically the minimum minimum level of quality for your code that you should strive for. To have your code structured in functions, to have your variables with meaningful names, and yeah, that's like a bare minimum you should do. Then you can expand upon that by basically putting comments in your code. As I already said, that's not only going to help you, that's going to help everybody else working with your code. And that's actually a way more likely scenario than you might think, because if you write some specific routine even to analyze code, it's quite likely that your PI might at some point advise another student to use the code you just wrote because you wrote that like 1 year earlier, and that other student should be able to use that code instead of basically having your PI to invest the time of that student now again to redo the same code because your code became somehow unreadable over time because you don't remember what it did in the first place. So what you can add is comments to your individual functions. You usually start with a comment on what the function does, like extracting power. You can comment your individual parameters, and you can comment on the return. And you can put input and return arguments here. For example, I really like knowing that the sampling frequency in extract feature is a float. Theoretically, that algorithm could expect an integer, but it's a float in this case, and there's benefit in knowing that stuff in without having to go into the function. There's benefit in knowing that this function will return me an array of data, instead of having to go into the documentation of how SciPy extracts information here and what kind of variable type that might be in the end. That's like gonna boost your own speed of writing code and adapting new routines to whatever you've already written by large quantity. And then the last bad part of this code is we had this line here in the code, and that line was super long. And as you can see, that has a lot of parameters here, and therefore it got a lot of arguments. And what you can do in Python is you can put line breaks in here, and you actually want to do that because it again makes the stuff way more readable. And for example, in the first line here, we have the data, we have the sampling rate, and we have the window function that's going to be used for the FFT and the PSD calculation. Then in the next line, we have some parameters which correspond to window size and stuff like that. And then in the next line, we have again a separate set of parameters that are totally unrelated to the size of the window. So it even logically makes sense to separate it in 3 lines like that. Yeah, and I've already jumped across a lot of concepts and ideas now on how to organize code and how to make that more accessible. And now I wanted to basically introduce them a little more proper and explain a little more in depth. The first concept I wanted to mention is global and local variables. When you write a script and you have no functions in there, it just goes from first line and executes everything to the bottom line. Like the usual MATLAB script, for example. Basically, everything you do lives in the global scope, which means every variable only becomes by default invalid at the moment the program terminates, and that's really dangerous. On the other hand, if you had functions in your code and you would create a variable within a function, the moment that function returns some value, thereby the function being exited, that variable doesn't exist anymore. It ceases to exist, and that's really handy. For example, if you do a lot of stuff in your code, you get a lot of different features from data, let's say, and you have more than one occurrence of a variable called data. And you have written all of that as a script. All of those data named variables are within that global scope. So you're running into the issue that you can never be really sure that you're not overwriting a variable that's going to be read later on, and thereby erroneously introduce a bug into your code. And that sounds really like not an issue if you have a 10 lines of code file or something similar. But then if you end up with something like that, even a 500 or 1,000 lines of code script, you really have to concentrate to not use the same variable named twice or something like that, to really avoid erroneously overriding variables that you're going to use later on. So the idea is basically to always encapsulate your functionality into specific functions, so you know from in which environment, in which scope those variables are supposed to be valid, after which scope they are supposed to be. After exiting that function, they're supposed to be invalid, and that's basically safety for you. And you would only ever use global variables labels if that's strictly necessary. Like if you have some global configuration parameter and that's called upon at a lot of points in your file, you need to make that global, but it should be done really rarely. And I've prepared a little example here where I actually want to highlight this very issue of having the same file name a couple of times. The whole file is basically, as I already explained, the global scope. And then within that file we declare the variable file name. and we declare it here, 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 and we have there another file name. And now the issue becomes knowing what the value of file name is at each point in the code is being executed. For example, when we run this code, file name gets first set to the character A. Then we run further, file name gets set to the word coding, and at this point we're going to print the value of file name, which is going to be coding. Then we're going to jump into the main function, which is going to be here. And by using the keyword global, we are not making file name a local variable, we make it a global one. Which means whenever we use file name now, we're basically going to override this one here, which is the same as this one. Then we are going to call some kind of nested function, and within that nested function, this time we again create a variable called file name. And as you may notice, there's not the global keyword again ahead of it, which means this time file name is going to be a local variable, which means this file name and this file name are separate entities. And that's important, because setting file name to is now is not going to override this file name here, because it's a separate entity. So when we print file name now, we're going to get is. When we're going to set file name now to create, then we return from that method and we print the file name now, we're going to get in the end coding is great. But I intentionally created this example to highlight why you would want to use functions, why you want to be a little bit careful with variable naming, and why you want to make sure that your variables become invalid after a certain scope, because you don't want to erroneously read wrong values or stuff like. So ideally, variables should, the naming of a variable, it should carry meaning. And if you need multiple words of that, which is actually something even I need to do usually, there's there's often cases that if I have a variable, I cannot express what this variable is doing with a single word. That's totally fine. Simply in Python you put an underscore between the individual words. And you can, for example, call it, what could it be, like power amplitude or something the like. Then your variable names, you should try to keep them compact. You don't want to have like 100 character variable names or something like that. You want to keep them small. But on the other hand, you still want for them to be to carry information. And also in Python, any variable name is small case letters only, meaning there's only and there's only one exception to that, and that's a global variable that goes in capital letters only. And that there's this kind of fundamental understanding that global variables are capitals only, whereas local variables are small case letters only, should already highlight the importance of not putting everything you have into that global namespace, because there's a really significant risk of erroneously, as I said, overriding or anticipating another value in the variable than there actually is. Next up, I have a couple of indicators you are not really good at, you're not really well choosing the names of your variables. Would be like generic names, which I really often read, and the favorite one is calling a variable temp, which is not telling me anything about what kind of idea it holds. Then another thing is very long variable names, and then increasing number in variable names. And the most common example would be temp1, temp2, temp3. Somebody else reading your code, having that written, for example, I would have no idea what temp3 might be, how that temp3 might be different from temp1. How should I know? But actually I should be able to decipher that from the difference of that variable names. Yeah, that's it about variable names, and then I wanted to talk about encapsulation, which is kind of the other big issue around here. And that's basically putting your, as I already said, putting your code into functions. And at the moment, with this code example here, we have everything within our main function. And we could actually structure that into a number of individual separate functions to highlight that that's actually different ideas. And as I already said, you're gonna greatly profit from that, and you're greatly gonna profit from having those identifiers here on what the input arguments are, what the output arguments are. It's gonna increase readability of your code by a long shot. A long way. And the question is, when do you want to encapsulate your stuff? Like, when do you want to put it into individual functions? When you have the feeling that there's a need to increase your readability, it might be because you have a lot of different functionality within one method. Or you want to separate individual lines of thought, like loading data and visualizing data. Or you have totally different functionality, which usually goes hand in hand with having a different line of thought. Yeah. And the last topic about how to structure your code is refactoring. And refactoring is basically revising your own code for maintainability and extensibility. And that's a little similar to what you do when writing a paper. When writing a paper, you usually, you draft your paper, you read it a couple more times, then you hand it to your PI, and usually your PI is really happy that you actually read it again and that you fixed a couple of early mistakes you made in your first draft. But especially in science, rarely anybody's doing that ever to their code. And in my opinion, the code that you use to derive your results is not any less important than the wording you had in your paper. Yet the wording in your paper is usually treated with more care. So you want to refactor your code. And you should refactor your code when you notice that your code has a lot of repetitions, like calling, like even having written the same subroutine a couple of times. If you've written the same subroutine 4 times, you could think about putting that into a separate function, which would decrease the likelihood of there being an error due to, let's say, a typo by a factor of 4, because you're not having it 4 times anymore, you're having it only once now. It's only only gonna make your code more reliable. When you have added some new routine to an already existing function, you wanna wonder whether you actually want to include that into this function, whether you want to make that new routine its own function. And then when you it becomes difficult for you to read your code, like for example that 1500 lines of code script file. You really want to start refactoring that into separate functions to make that again maintainable. Especially if you publish your results and then a reviewer asks you to change a parameter here and there. It shouldn't take you a couple of hours to figure out how to where to make those changes if those changes are trivial. And refactoring and helps you helps you a lot with that. And the last idea is basically if you have problems in your code, and I mean, of course, you're gonna know it crashed in line 40 because that's what your whatever you use for programming is gonna tell you. But still, you need to localize why it crashed in line 40, for example. And if you have serious trouble localizing where the error is coming from, it might be due to the fact that your code is very convoluted and would actually benefit a lot from being refactored. Having covered that, I actually wanted to how to structure your code and how a lot of how more code structure would benefit you. I wanted to shift a little from that to optimization, and the first idea here is to parallelize execution of your code. And this is kind of an example I wrote to highlight that. We have a main function here, and we have a function which gets looped. In this case, we're just going to wait a second within that function to basically say that whatever we do in our function, it takes a second. Usually, of course, you're going to do some kind of data evaluation, but again, that takes time, and mimicking that by waiting a second is just convenient at that point. So if we loop 20 times through that looping function here, we basically have two ways. Either we can go into the we can now go into the non-parallelized part, which means we're just going to loop through that loop 20 times, which then nets to 20 times waiting 1 second, waiting 20 seconds. Or we can run that in parallel. Have basically 20 processors, wait 1 second in parallel, which nets us an execution time of 1. So we would have a speed up of 1, speed up of 20. Which is pretty significant, and usually you have a lot of different when doing your analysis, you have, like, if you do EEG stuff, you have a lot of different channels. Even if you do single channel stuff, you usually have a lot of patience. In my experience, there's never the issue that you have really little data. It's 9 out of 10 times rather the opposite. And having a somewhat modern PC with like 8 or 16 processor cores in there can grant you, let's say, if your algorithm otherwise takes a week to execute, if you parallelize that across the your files, for example, it might only take you a day or half a day in the end. That's going to be a significant difference, especially if you like later on figure out that there's some mistake in your code. You're not going to lose a week, you're going to lose half a day. Yeah. So parallelizing is easily done if you have some kind of loop here, and we're likely gonna look into that a little more closer next week when doing that live coding session, how to apply parallelizing to speed up processing. Anyway, when doing some kind of parallelizing, you should always be aware of the impact on the memory. Like, you want to parallelize as you want to basically do in parallel compact parts of your code, meaning that you don't want to have to copy all data into every process and then run it through there, because that's 9 out of 10 times that's gonna exceed the working memory you have on your PC. So you only want to copy the least required amount of data. And you want to choose an efficient angle for that parallelization. Like, if you had, for example, for some odd reason, you only had 2 patients, you usually wouldn't want to parallelize across patients if it's 2, because there would only be a potential speed up factor of 2. It couldn't be any faster. But if you had 10 recordings for each of those patients, you could do those 20 recordings, for example, in parallel, thereby having a speed up of 20 instead of 1 of 2. So you always want to look out what's the angle then doing that parallelization, and what might be an efficient one. And the third one, you always got to keep in mind that if you, for example, parallelize, let's say, across files, and those files have different lengths, that parallelization is only going to be as fast as the slowest individual process. So if 9 out of those 10 files are 1 minute and the 10th file is an hour, you're not going to profit much from the parallelization at this point either, because the longest file is so much longer than the other 9 ones. So you're not going to get a speed up of 10. You're probably going to get 1 at all. So you would have to choose another angle to parallelize that, and there's usually plenty of opportunities to choose from. Yeah, and other means of increasing the efficiency of your code would be that when you do floating point arithmetic in Python, it usually always goes for 64-bit floats, which is way more than you need. For example, if you create a numpy array and you turn that into 32 bits, you get a speed up of up to a factor of 2, because you're only having half the number of bits in your individual variables. You want to remove repetitions. Like, if you did, for example, a power density estimation, and later on you did some connectivity stuff, there's the option that you could move all your data into the frequency domain in the first place, and then in a subsequent step do the power estimation from that data already being in the frequency domain, and doing the connectivity stuff again with the data already being in the frequency domain. There's no point in moving it twice into the frequency domain. So that's basically what the removing repetitions part is about. And then another topic I wanted to talk about today is testing. And usually when testing your code, you have a couple of different ways on how you could do that too. One way of doing that would be you can test your individual functional block, which would be like testing a specific function or part of a function. And that's actually something you should do. You should always be aware of whether this segment of code or this function is actually returning the value you were looking for in the first place, instead of blindly writing it and hoping that that the code executed fine because it did not crash. The code not crashing doesn't necessarily mean it produced the output you were looking for. It just means it produced any output without having basically a catastrophic error. Doesn't mean that the output is meaningful, and that's basically what you're gonna check. Could check with those individual function tests. And they are usually called unit tests. Then you have then you can have some kind of integration test. An integration test would be that you have like two individual functions and they interface in some kind, like loading data and then visualizing it. And you want to test whether the data being outputted from that one function gets correctly passed into the next function. And then you could go even one step further in the end, and you could do a system test. And a system test is basically to test your whole setup, whether it is not setup, your whole code program, whether it's reducing an expected output. And what I, for example, like to do for that is, if I have for let's say EEG data, and I have some movement data and I have some rest data, I always like running that EEG data through a power estimation through the same pipeline I use for doing all those other kinds of analysis I do with my data. I get the power in resting state, and I get the power during the movement. And then I know that during the movement, the beta power over the motor cortex should be decreasing in compared to the rest state. And by checking whether this is actually the case, I can do a systems test basically. I can test whether my data got loaded correctly in case of this example. I can test whether the power estimation was correctly in this example. I can test whether the visualization worked properly in this example. Of course, that doesn't mean like everything is correct in the code, but I can, from this test, I can at least tell whether there's some kind of mistake already in the power estimation or not. And going for markers that you are really aware that they have to be there, ideally ones that are unrelated to what you're looking into in the first place, can really like help you in getting a understanding on whether your code is actually valid or not. And then let's say there's some kind of bug in your code and it didn't turn out the way it should have been. What you can do then is called usually debugging, and you're probably gonna see that a little closer next week. And the idea of debugging is basically that you set a breakpoint, which at least in Eclipse and with like every other develop environment I've seen so far, you click right next to the line of code you wanna basically your program to stop executing. Then you always have like an end life symbol somewhere, and then you execute your code, and it executes just until the line that you just highlighted, and it stops immediately there. And then you can see what the value of the variables at this point. You can go step by step and try to figure out why the code is not returning the output it was supposed to generate. And another really handy tool when working besides the debugging stuff with code, besides the debugging stuff, is version control. And the concept of version control is that you write code, and then let's say it's 5 p.m. and that's it for the day. And then when you come in the next day, you want to make sure that you have an option to fall back to whatever you had yesterday. And that also applies to the other days. And by progressively working on your code, of course, you're gonna at some point achieve whatever you wanted that code to do in the first place. And version control basically allows you to jump back to individual earlier periods in that code. And that's really handy. Usually, you would create a you would call it a new version of your code if you like added a new functionality, and it can be like totally minor. It can even be that you added a comment or you just changed the name of a couple of variables. It doesn't really have to be substantial update or something. Anything that you seems basically that you basically feel warrants making a backup would be called a separate version. And that's something you can do with JIT, which also comes with a GUI on Windows and Mac. And what you basically do is you write your code until let's say 5 p.m. and then you can say, for example, JIT add, and you can put go with either filename or dot to add all files. Or you can do that in the GUI. You can commit it and you can push it. And what that basically does is it takes the code you had at 5 p.m. and basically makes that into a version. And if you then come in the next morning and you like change a couple of variable names because you think that those new names are better fitting than the old ones for whatever reason, and now nothing is working anymore. You, for example, got the option with git stash to like just undo all changes, go back to whatever you had yesterday evening, and work from there on again. And by using some kind of version control system instead of any other option, which would be like to have a plethora of individual folders, usually with a underscore and copy behind them or something like that, is that it's way easier to work with that kind of system, because even if I do my code and I do my developing, I use that kind of thing and I end up with between a couple of hundred and a couple of thousand pushes with individual minor changes. And as I said, that can be as minor as adding a comment or something. And it really helps to be able to fall back to even the version you had last month, because you knew last month that was working and now it's not working, without having that need of having basically 1,000 individual folders, and then you would have to try to figure out based on folder creation date what kind of version this code is. So it really helps you organize your own stuff. And there's actually plenty of tutorials online on how to use JIT or something similar, and managing different versions of your code and iteratively building to the version you want to have. And another topic for today about coding with Python is using some kind of integrated development environment, usually called an IDE. And what I've been using so far is Eclipse with PyDev. You can also use Visual Studio for Python, which is Visual Studio is from Microsoft, and I think it might also be available for Mac, if I'm not mistaken, but I don't think it's there for Linux yet. And you can, for example, go with Spider, but I think if I were you, I'd rather go with Eclipse or Visual Studio. The reason being that Eclipse and Visual Studio, from the day they are set up, they promote that programming style of having different lines of different ideas of code and different functions, using different files, and they're actually promoting that structuring, and that's basically helping you to self-discipline yourself a little into applying that structuring. And Spider, on the other hand, is very MATLAB-like, and hence it promotes that style of not promotes, but it also supports that to a much larger degree that style of writing those super long scripts, which which are gonna bite you at some point. So Eclipse, I mean, just wanted to show them quickly what you've already seen. And then there's Visual Studio, which looks pretty similar to that, and both of them are really good. Eclipse is a little bit like the ugly uncle of Visual Studio because it doesn't have the same funding behind it, but that's another story. Yeah, and I'd recommend, if you do some coding in Python, to go for either of these two. And there's, of course, Spider. So that's it for today's programming session, and as I already announced in the beginning, next week we're gonna do some live coding, and that's gonna start with downloading Eclipse, making installing PyDev within Eclipse, getting some data loaded, processing that data within Eclipse, and then having some kind of visual result. And yeah, thanks for your attention, and